My name's Erika. I live here in San Francisco, and just about a year ago, co-founded Spark Climate Solutions, which is a new nonprofit focused on helping to accelerate progress in neglected but really high impact climate fields. And that has led us to an initial focus on methane. So I figured for today, since my impression of this group is that it's a really broad audience within methane, that while everyone here is, I'm sure, on board with the need for methane mitigation, I want to talk a little bit about how we view the methane system, because I think it's pretty unique. And I'll go through that. So I'll spend a little bit of time there, and then spend some time talking about our first two focus areas. Great, here we are. So what is Spark? So we're building climate solution ecosystems in neglected high leverage fields to repair the climate. I started about a year ago, and we are a small but growing nonprofit. Some of us are based in the Bay Area. We work actually a lot with folks at Stanford, but we're a distributed remote team currently across the US, but looking to grow internationally as well. So I want to talk about the big picture of methane and how we view the overall climate system, and therefore why we're focused on methane as an initial spot. So this is directly from IPCC. We can see kind of, roughly where we are temperature-wise today. And the bad news is that we are not on track yet to limit ourselves to a 1.5 C consistent pathway. And so, we don't know exactly where we're heading, but we should be prepared for the possibility of being somewhere in the 2 to 3 degrees C range while we do all the work we possibly can to avoid that future. And the challenge that we need to start grappling with is that with that as a possible future, we start to see even more major human impact and Earth system risks that we're not prepared today to manage. On the Earth system risk side of things, one of the important aspects of the 1.5 degrees C guardrail is that it helps to decrease the probability of various natural system feedbacks and tipping points. As our understanding of these has improved over time, we've realized that actually the Earth system sensitivity kind of kicks in at lower temperatures than previously believed. And so we're already in the danger zone for some of them, and will increasingly be so until we stop and then reverse our current upward march of temperature. So we're very action-oriented people. And so the question is, okay, that doesn't sound good. What do we do? How do we help to fix these many, many challenges? And so what we're focused on right now are places where we see really underdeveloped pieces of our climate response. So I think this is something that everyone here is probably very familiar with. And this is just the contributions today of different greenhouse gases to current warming. And to many audiences, this is actually a big surprise. Carbon dioxide has gotten so much of the attention, and deservedly, that we do sometimes forget that the majority of warming is actually currently from non-CO2 sources. And if we're really going to pull all of the levers that we need to in order to mitigate temperatures in both the near term and the long term, we need to be working to cut all of these. Fortunately, that has more broadly entered the narrative in the last few years. The challenge, though, as we dig into methane, is we have very distributed sources, and we don't have solutions to many of them. This is all methane sources, including naturally anthropogenic. I'll have a better, this is an old slide. I have a better version of this in a few slides. We don't need to cut 100% of natural methane emissions, to be clear. But if we just focus here on the anthropogenic side of things, these yellow wedges are showing projected 2030 emission levels per sector. And yellow is those that today we model as there being economically feasible ways of mitigating. Orange shows areas where we have solutions that are technically viable, but not yet economically viable. And red represents areas where we don't have any available supply side solutions today. And so one of the things that jumps out here is that we need a lot of innovation, right? We have a lot of stuff in red that we don't have available solutions for. And the stuff in orange, we have this sort of dashed line halfway through, who knows, but where some of this is incredibly non-economically feasible, it's probably, may not be realistic right away, and we're still depending on further innovation to help with down costing to accelerate our path to deployment. And so in the broad narrative, I think many people, reading the New York Times, for example, think that methane means oil and gas methane. And that is a really critical component to address. And it's where we're going to get many of our first wins, because we do have so much oil and gas methane that we have solutions for, we can start deploying today. But what Spark is focused on is really looking at this whole picture and how can we accelerate these areas where we do need solutions, but it's going to be a longer timeline. But if we don't start really investing today and accelerating those timelines, we're going to be looking at a similar graph like this in 10 or 20 years and kicking ourselves even harder. Another piece, obviously, of methane overall is natural emissions. Methane has, we've always had some natural methane emissions. We are currently dramatically expanding our methane emissions through anthropogenic sources, but there's also increasing evidence that the warming that we have already caused and are projected to, unfortunately, continue causing for at least some amount of time is increasing those natural methane emissions. So this is, it has the reference here. This is from a paper from a few years ago, looking, they took a biogeochemical methane-enabled Earth system model and played out with the natural methane emissions that were modeled, what natural methane emissions might look like across 4 different categories: wetlands, fires, termites, and then an increase in the soil sink. So that's a mitigation to the increases in emissions in the other categories. They explicitly excluded permafrost, and they implicitly excluded other potential sources like clathrate. So those are not included here. And so the place where this gets even scarier is that we are already seeing and expect to further see increases in natural methane emissions that we don't have direct mitigation options for. And to make things hairier, this is relatively new work that hasn't yet been included in IPCC climate models. And so when we look at what a 1.5 or 2C consistent pathway is, we're actually not, that is not taking into account these potential elevated natural methane emissions. And from some late night magicking with these models, this is not a referenced number, but it looks like this probably is on the order of about like 0.3 degrees C of additional warming, just taking these numbers and throwing that into magic. So to put that all together, we see on the left-hand side here, and I'll explain these scenarios, but sort of a natural methane emissions scenario under SSP 1.2.6. These are the same paper that I'm referencing from the last page, this Kleinen paper, and on the right-hand side, SSP 2-4.5. And the way to read this is that if we just look at the elevated natural methane emissions from the sources that were modeled, so wetlands, termites, and fires, plus an increased soil sink, what we see is this big green block being added to our overall elevated methane emissions. And that, becoming a very large portion of our overall emissions. On the anthropogenic side, what I'm showing here is current emissions or historical emissions in 2015, and then in 2050, looking at the Haugland-Isaacson paper of the modeled maximum technically feasible reductions. So the 2050 numbers here you're seeing are, if we model out baseline methane emission increases and then remove everything that we have technically feasible solutions for today. And so if in 2050 we're only emitting the stuff that we don't have technically feasible solutions to mitigate, how much methane would be left over? And the really bad news is when you look at that, you're not seeing a dramatic cut in overall elevated methane emissions. In 2100 here, I've shown the same natural methane emissions from that same paper, and I just have the same number from the Isaacson paper just to sort of show what that curve may look like, though that hasn't been modeled as much. On the left-hand side, that star is where an SSP 1.2.6 model would want to see total elevated from these sources and anthropogenic methane emissions to be. So that's our target. That's our 2100 target. And as you can see, we've got a lot of work to do, made worse by these rising natural methane emissions and made already challenging by the many sources for which we don't yet have solutions and need to get on that so that we do on these timeframes. What this all ends up meaning is that, today we see methane being our largest deviation from RCP 2.6 models. And while we know from a climate system point of view that we need our methane concentrations atmospherically to be on a sharp decreasing path, they are stubbornly marching up every single year. And we need to figure out how we reverse that trend. The other side of the methane equation, we have our sources and we have our sinks. So methane is naturally oxidized. That's why it has the 12-ish year half-life in the atmosphere. It's a natural chemical process that occurs today, mostly in the atmosphere through the hydroxyl radical, but a little bit in atmospheric chlorine. And then there's also some soil uptake. And the soil uptake is modeled to increase a little bit over the next few decades, but would still remain, a similarly small overall fraction. The great news about the fact that methane does remove from the atmosphere is that we have the opportunity, if we're able to fully address methane and really dramatically cut our emissions, to have a decreasing atmospheric radiative forcing impact in a way that cutting CO2 emissions doesn't do, because it's a stock gas, or at least not on as short of a time. And so that is why we're thankful that methane naturally oxidizes and has a short lifetime. And our climate models and our ability to potentially have any hope of staying under 1.5 or 2C guardrail really does depend within the models on these sharp methane decreases in order to bring that sort of radiative forcing bar down. There's some added color here for why, which is that as we cut CO2 emissions, obviously critically important, we need to get off of this constant upward march of temperature. We are expected to see a short-term bump in temperatures as co-emitted aerosols are also cut. And the greenhouse gas dance, as I like to call it, that we need to execute over the next few decades is, while decarbonizing as quickly as we possibly can, also making sure that we're cutting methane as aggressively as we can in order to counteract that near-term bump, and in so doing, be able to manage both near-term and long-term warming in parallel in a way that decreases overall climate risks. There's that bump. I won't labor that point. And yeah, if we don't do this, it makes a really big difference. So we can't sort of cut any piece of this puzzle. We need to be cutting every greenhouse gas as aggressively as we can. And methane has a really big role to play in limiting our peak temperatures and starting to sort of reverse the trend while we hopefully scale up massive CDR in parallel. Our near-term warming matters a lot for a bunch of reasons, both in climate system impacts and human system impacts. And so there's a value in limiting peak temperatures, and there's also value in sort of smoothing the curve to get there and decreasing the rate of change and methane does all of that and more for us. So that's just a quick snapshot of kind of how we think about the combination of anthropogenic and natural emissions, and kind of where that puts us in terms of additional priorities that need to be added to the system to complement the incredibly important work on CO2 decarbonization and the incredibly important work on deploying the available methane mitigation solutions that we do have. We're working to help complement those existing strategies in areas where there's a lot less focus to date, but we know that we need to get started so that hopefully we will eventually be in a no deployment situation there as well. So the areas that we are trying to focus on at Spark are atmospheric methane removal. So this is a potential method of helping to address elevated natural emissions as well as historical emissions. It's very closely intertwined with methane emissions destruction. So this has also in the past been called point source methane removal. But the idea here is there may be oxidative technologies that can be applied to destroy oxidized methane before it enters into the atmosphere. And anytime that we can reduce an atmospheric emission, we absolutely can. And that is another space that is very early in its overall development timeline. And then the second sort of broad category that we're focused on are enteric and livestock emissions, for which we have some technical solutions already on the table, but as we'll go into later, are only starting to kind of scratch the surface of both what is likely possible and also what is needed. Before we talk about those two areas, I want to talk a little bit about the Spark model and how we approach these areas, because it's relatively unique and weird. So the way we think about these areas is that our goal is to help support these fields being grown. This needs to be an all hands on deck effort that's going to take many people and many organizations over time. And so the role that we can play is helping to roadmap what needs to happen in these spaces and jump in the very early days to help align the field, start pulling more resources into the field, support the players who are already there, and create opportunities for more people to join these fields, grow coalitions, and then as we start identifying gaps with each of these communities, help to spin up the many efforts that are going to be necessary in order to have these become flourishing spaces. And that can take a lot of different forms, and happy to talk about this more at the end, but this can look like helping to spin up new projects, sometimes with other organizations. Sometimes it looks like spinning up entirely new organizations where there's work that needs to get done that doesn't fit into any existing organization for any reason. And then also doing a lot of regranting. To date, we have mostly been doing research regranting, but over time that will shift to be more nonprofit regranting as well. So we would take inspiration from some really interesting work that has happened in the ocean CDR field over the last few years as a proof of concept for this model. And so the big kind of shift here over the last 4 or 5 years has been, I'd say on the left-hand side, it was operating out of a place of scarcity, of funding, of opportunity, of people working in the space. And it wasn't yet sort of coalesced and organized into a field that was very well funded, that funders understood how to interact with. And so what we saw was kind of bits and pieces of things happening, but not yet hitting sort of the critical mass that was necessary in order to have the big leaps forward that then fed that flywheel of interest and support that then allows you to, run enough experiments to have the ones that work out really well. And the shift has been over the last few years that now it's a much better supported space. Philanthropic funding has expanded greatly and continues to expand. There are multiple nonprofits who are helping to support different parts of the field and advocate for it. There's a very supportive National Academies of Science report that's pushing for further government research funding in this space. And it's becoming an exciting space where people want to be. And we know the folks well who have been behind this, and some of the lessons learned from their experience is really the value of helping to build the field, coalesce the vision, both to support the folks in the field and also to be able to more clearly educate folks outside of the field about what the potential is. And by doing that, you can help get out of that scarcity mindset, because that makes more funders interested in have a pathway to actually knowing how to deploy capital. Then you get more research progress, and sort of that flywheel continues. So that's how we're approaching the fields that we're working in. So the first field is atmospheric methane removal and methane emissions destruction. Just as a quick reminder, methane is currently oxidized in a number of different ways, primarily atmospherically. And we think there's a few really important reasons why this is an area of study that is important to accelerate. As mentioned before, we face the risk and the likelihood of increasing natural emissions that we don't currently have other solutions for, and the oxidative capacity of the atmosphere is very complex and does not scale with increasing emissions. And so we're already seeing and expect to continue to see that the atmospheric lifetime of methane that is emitted will increase somewhat. In terms of terminology, this is the terminology that we're using, and I think it's also useful to share to put in context where we see both methane emission destruction and atmospheric methane removal play in the overall ecosystem. So when we think about methane emissions reduction, there's two very high-level ways of doing so. Don't produce the methane or let the methane sort of out into the system in the first place. And then the second thing is, well, kind of capture it and destroy it right before it enters the atmosphere, even if it was produced. So just to use one example here, there's multiple different examples of how this concept applies, but let's just choose landfill one. We can reduce food waste so that we're not producing as much methane in the first place. That's great. That's methane avoidance. We should do that as much as we can. We can also change sort of landfill practices to decrease the methane production of those environments. Great. We should do as much as we can. Sometimes, though, the methane avoidance solutions we have are not fully sufficient. And so a complementary set of methods can be things that destroy or use that methane before it enters into the atmosphere. So the well-known example here, obviously, in the oil and gas space is flaring. That's sort of this concept, and there are analogies to that already do apply or are being researched for other sources. The primary difference between sources is concentration. And so a lot of the work in this space is going into how do we create things like flaring in very rough concept, and that it's destroying methane before entering the atmosphere. That works for much lower concentrations, and that is a very different technical challenge, and one that many folks at Stanford actually are working on. And then when we think about atmospheric methane removal, we're really talking about removing or destroying methane once it's in the atmosphere. That should never, ever be a replacement or a substitution for all available anthropogenic methane emissions reductions. But we do unfortunately know that natural sources have a risk and a likelihood of being on the rise. And we already also have about 0.6 degrees of methane in the atmosphere from historical emissions, which go away slowly. And so atmospheric methane removal could play a really important role in that space. These solutions could take many forms. These are all, I'll show it in a second, but these are all at very different sort of TRL levels today. But I think the important thing here is methane removal is not one thing. There are many different methods that are being studied, and the considerations for each of those will end up varying a ton. Because of the state of the field, we also don't know which ones will pan out yet. So just to sort of illustrate a few different kind of flavors and intervention points, right? So on the left-hand side, we have methane emissions destruction. So conceptual model here is, destroy the CH4 as it exits the proverbial cow barn before it enters into the atmosphere. That's methane emissions destruction. And then we talk about atmospheric methane removal. Again, a few different methods potentially that could be connected with direct air capture. Some of them might look a lot like engineered systems using thermocatalysts or photocatalysts, for example. And there are also methods being studied that are atmospheric. And again, because these could take such different forms, over time, governance and how they're treated will need to vary based on the particulars of the particular method that we're talking about. So this entire field is at a very early stage. So there's a number of methods on the left that are under development today. And what you can see here is that for everything below 2000 ppm, we're at very early TRLs, there's nothing yet commercialized. And it's only when we go up to greater than 2000 ppm that we have commercialized solutions in the form of thermal oxidizers and flaring. So I think it's really important when we talk about this that we're very clear that we don't yet know what's going to work at what scale. This absolutely cannot replace all available methane mitigation options that we currently have. But hopefully, if we're able to push forward this work successfully, we'll be able to add future tools to our tool belt to help with these risks in natural methane emissions and in sort of stubborn anthropogenic emissions for the case of methane emissions destruction to further bring down our atmospheric methane levels. So in terms of sort of field building, what Spark is currently doing in the space is we were organizing big research programs and funding those to accelerate pieces of this work, and we'll be scaling that up a lot further this year. We're organizing the first methane oxidation research convening that some folks on the line here will be attending. We're building a research roadmap collaboratively with researchers in the field, and the convening will be part of that process to the point of the overall community building and having a shared vision. It's been recently announced that there's also been a National Academies of Sciences report, particularly on atmospheric methane removal. That is a process that's getting kicked off right now. And so engaging in that process and also helping sort of support the scientific community and preparing for the public workshops that'll be coming this summer in the field, and then engaging the federal government on priority research needs, because if we project out sort of the research roadmaps here, we pretty quickly get outside of the scale of what philanthropy will be able to handle on its own. I see two things in the chat. I'm just going to check. Okay, cool. So field number 2 we're working on is livestock enteric fermentation. So cow burps, not a bit of a joke. It's a real thing, a real problem. So why do we care about this? You kind of already saw it in the previous slide, that big purple section that we don't have full solutions for, but it's largest anthropogenic source of methane, where we don't yet have supply side solutions. And on its own, it could be contributing modeled about 1/4 degree Celsius by the end of the century. And the solutions ecosystem is very, very early days. I caught the graph of this, just goes to my slides, but if you look at the RCP 2.6 methane profile, enteric emissions will consume all of it without additional technical solutions found. And as you saw, as will the elevated national emissions that are not modeled in. So these are both critically important to solve. So enteric, it's the largest anthropogenic source of methane, and yet incredibly little funding is actually going towards it. So there's an estimated $1 to $5 million a year in US federal funding going towards finding solutions here. They're somewhat more internationally. New Zealand and Ireland have been big leaders here, but we're still talking about really shockingly low budgets compared to the need and the impact here. In terms of the current solution space, the solutions that are becoming available now really focus on cows that eat what's called total mixed ratio feed, because they're feed additives. And what that means is that they work for the portion of cows that are in barns where someone's feeding them every day. And in the US, it's about 30%. The global data is really messy, but it's less than about 10% globally. And in terms of approved solutions that have been approved anywhere, that would be 3-NOP being approved in Europe. It cuts about 30% of methane. So in the US, we're looking at about 10% of methane can be addressed with current solutions. However, 3-NOP has not yet been approved in the US. So that number is lower to zero here for at least feed additive solutions. There are also practice changes that can make somewhat of a difference here in terms of just changing what the actual feed itself is without any so-called additives. The challenge here is that enteric emissions on their own are projected to increase as more folks become wealthier and desire meat, which is on its own fine and good. But what it means in terms of methane and climate impacts is that if we don't help address the many challenges, particularly with beef and other meat sources, that even if we fully deploy the solutions that are already on the table, we'll basically be at a standstill, where our methane emissions reductions per cow are made up for by more cows. And so we need to act. Quick way just of thinking about cows is, you want to lower reduction, you want to decrease emissions per cow for as many cows as possible. And the fewer cows there are, the less that those total numbers are going to be. There are many different approaches here. We are currently focused in this space on reducing the methanes per cow for as many cows as possible. There are other pieces of this overall equation. And so one of those is reducing meat and milk consumption. That's going to play an important role in this overall ecosystem. We strongly believe that even with those approaches, there's going to be a lot of cows left globally, particularly on the timelines on which we would want to see methane mitigated as much as possible. And so we want to make sure that those remaining cows are as clean as possible. You also, might see methane removal solutions where we don't want all of our eggs in one basket here. That's not a very good risk reduction strategy. And so, the goal here really is reduce the methane from the cow. And the next decade is critical to do that. So if we kind of go back to this, what are our climate goals? From a climate system and greenhouse gas perspective, we would like, in order to mitigate, peak temperatures and radiative forcing, to be able to minimize atmospheric methane by 2050. And we work back from that and sort of, looking at agricultural innovation and agricultural deployment timelines, we basically end up with this is the decade for innovation and R&D, because it'll take a while to have that translate into atmospheric methane reductions. And so we need to start now and start investing. The good news, I guess, is that there are a number of places in the microbiome to intervene. And there is increasing levels of research going into various of these solutions. Because it has been a small, relatively underfunded field, there's also a lot of potentials here that have not been fully explored yet. The other good news is that methane is a waste product of the cow. It doesn't rely on it. It would actually be more productive or could have potential to be more productive if it was no longer producing methane. And so there's a really big potential here for a win-win between both decreasing climate impact and also increasing cow productivity, which have benefits on decreasing land usage and just a benefit to farmers which could help to accelerate future adoption. The current state is a lot of challenges we're trying to think about and work on. Measurement is still incredibly sort of expensive and bespoke. And so one thrust of our work is in helping to decrease the cost of measurement so that we can be measuring a lot more because you fix what you measure. And also to support both large-scale research programs as well as future monitoring, reporting, and verification. We need to be able to measure this stuff and not have that be such an expensive proposition that we do it in very limited capacities. Because of the expense and bespokeness of these systems to date, we also see that globally that they have not been broadly distributed. And we really, this problem comes with a lot of regional variation in terms of different breeds of cows, different feeds, different climate conditions. And so we're going to need to build this capacity globally. We don't yet have any anti-methane silver bullets. We likely will never have a true silver bullet. And so a lot more solution development and fundamental scientific understanding of how the microbiome is working in cows and therefore places we need to intervene needs to happen. And we'll need to figure out how we can support global distribution of these solutions, both to support those that are already available and support additional ones that hopefully become available over the next decade or two. And that is also work that takes a lot of time to sort of build the inroads for, so that hopefully we can deploy solutions that we have as quickly as possible to start actually bending that curve the way that we all need to. So what we're currently doing in the enteric space is we're doing a lot of internal road mapping of kind of the many different factors here. One of the things that helped highlight for us pretty immediately was that there was this huge gap in R&D funding, and that was a place that we could be really additive. So we're doing federal engagement around the R&D funding priorities that we've identified. And as I mentioned, we're also incubating some work on agricultural methane and nitrous oxide measurement in order to support research efforts, improve our monitoring and understanding, and get more data. So with that, just sort of quick recap, and then love to jump over to questions. So yeah, Spark is a very new NGO working on building these high impact climate solution fields that we see as needing a lot of additional support in order to accelerate. And the way that we do so is in really looking at how we can deploy all levers in order to achieve the eventual goal, which is decreasing greenhouse gases in the atmosphere. And some of our future work that we're looking at is also thinking about how do we decrease the human impacts of those climate changes. And yeah, also kind of a unique model in the way that we can the way that we're set up to support other organizations and projects and sort of building out this ecosystem. And things that I didn't talk about today, but just things that we're broadly interested in thinking about in case these are things that you're broadly interested in thinking about as well and ever want to talk about these things. In general, we're interested in all neglected solution areas that will be complements to the really important work that's already happening in decarbonization. We're looking at other methane sectors, looking at other non-CO2, non-methane sectors as well. We think about this framing of decreasing risk and uncertainty in the system. So for example, methane removal can play an important role in both decreasing fundamental Earth system risk by decreasing atmospheric methane, and therefore, potentially lowering the probability of hitting some of these natural feedbacks and tipping points, and also could play, potentially, if it works at scale, potentially could play a role in responding to some of those changes that do emit more methane in order to avoid positive reinforcing feedback loops in a way that would sort of bring that part of the risk of the system down. We think a lot about near-term warming and long-term warming and how we make sure that we're developing the solutions and supporting them in such a way that we are accelerating both goals in parallel. And also thinking about how we can protect against some of the worst possible outcomes through both mitigation and adaptation, and looking at where the places where we don't have plans yet. We don't even sometimes have the scientific understanding of what is going to happen in order to be able to plan for it. There was one more slide I was going to add, I forgot. Well, that last slide is feel free to reach out. I'm Erika at sparkclimate.org. Our website is sparkclimate.org. There's a contact us page that goes to my email. I read them all. I respond to all of them. It's spam. And we're also hiring a bunch. So if you're interested in these fields or this general approach to field building, I would love to hear from you. And if you're working in any of these or related fields, and you feel like you either have a piece of the puzzle that we're missing and want to talk about that, or you have an idea of something that should be happening, be that within Spark or an important research priority that you maybe need support for, again, definitely feel free to reach out. We're really excited now that we're gaining steam to get a lot more involved in all parts of the methane community and help support all of us in achieving these really hard goals, but really, really important ones.